10 and 11 is about energy. Uh, the the lecture in the morning was awful, so hopefully it will be a little less awful today, this in the afternoon. And it was not the class. There was nothing wrong with the class. It was me. I was, I guess, too tired, but it was really, really bad. Not, I didn't understood myself. So yay, yeah. Let's hope. Let's hope it goes a little bit better. Uh, I'm still tired, so I'll do my best. Uh, so, chapter 10 and 11 is going to be about conservation of energy. You probably have already seen a little bit of conservation of energy, especially when talking about chemistry. Every time you do any kind of chemical reaction, you are doing, in a sense, some kind of conservation of energy, and you have seen some of the laws of conservation of energy already. Uh, for this part of the semester, I'm going to be focusing not so much in conservation of energy in terms of chemistry. I'm going to be doing conservation of energy in terms of mechanical systems. So this is going to be a little bit detached from the human body and biological systems. But the principles, I think, can still apply, and I'm going to try to connect it at the end. But right now, what I'm going to try to explain is how you transform one kind of energy into another kind of mechanical energy, and how you calculate efficiencies, and how can you quantize those things. Okay, so that's what we're going to try to do. Chapter 11, we're just going to touch it very briefly, and we're going to spend most of the time on chapter 10. Okay. If we're done with this, this is going to be pretty much everything that's going to be in your second midterm. So your second midterm will be from elasticity and deformation, conservation of momentum, and conservation of energy. That's going to be the three topics on your exam. Okay. Okay. Oh, I don't have a pen. Oh, yes, I do. Aha. Okay, so we can assume that we have systems, and that all these systems, just because of the own nature of the system itself, it's going to have some kind of energy. Okay, so we can have systems that are isolated, or systems that are non-isolated. Systems that are not isolated means that they don't interact with the surroundings. They don't do anything. Everything that's going to happen is going to happen inside these boundaries. These boundaries are kind of imaginary. But for example, let's say that we are analyzing, or we're trying to figure out a kid is falling from a cliff, and we're trying to figure out how fast it's going to hit the ground. So the system will be the kid, the cliff, and the ground. We don't care if the kid is screaming. We don't care if it's not screaming. We don't care if it's rainy. We don't care if it's sunny, because those things don't accept the fall. Okay, so when we're talking about the system, we isolate the system in terms of the things that matter for the problem that we are working. Okay. Sometimes we can interact with the environment, and in those cases, we say that the system is not isolated, and we're going to talk about how can we interact with the environment. Okay, so in an isolated system, one of the things that we care is that if we have some amount of energy, it doesn't matter what's going to happen, the energy has to be conserved. And that's one of the fundamental laws of physics. And it basically is that in an isolated system, energy is conserved. Okay, that the change in energy is going to be equal to 0. So the energy doesn't change. Or if you were to see it another way, the initial energy that we have is going to be equal to the final energy. So same way that we were working with momentum, that we have a before and an after, or we have an initial state and a final state. The same thing we're going to be doing with energy. We're going to have an initial state, and we can measure the energy at the initial state. And if the system is isolated, it doesn't matter what happened in there. The energy has to be conserved after an event. Okay? That's more or less where it is. Now, what happens when we don't have an isolated system? When the system is not in isolation, the energy can change. Okay. Now, when the system change, it can increase or it can decrease. Okay. And we have a very specific name when we're talking about mechanical energy, and we say that the work is going to be the change in energy, and this is work. And it's a specific kind of work, it's a mechanical work. Okay, so I can do work into a system, and when I remove energy, and that system is going to be doing some work. And we're going to talk about later about the definition of work. It's very specific, but it's just that work is a way we can either add or subtract energy from a system. Okay, specifically talking about mechanical work. Okay, there's another way that we can add or remove energy from the system, and it's through heat. So we can also add through heat. Okay, the basic case is you have a glass of water, and the water is going to have some energy. Just because it's not at absolute zero, there's going to be some kind of energy in the water. You can add energy to that water by just adding heat, just by putting it on a flame. Just by putting the water under a flame, or a flame under the water, and you start heating the water, you are adding some kind of energy into the water, and the water is going to increase its temperature, and it's going to start bubbling, and then it's going to transfer into transition into a gas. So that's one way that you are adding energy into the system through heat. You can remove energy through heat the same way. Like if you have an engine and the engine is running, you are extracting the energy from the fuel, and the fuel is moving the mechanical parts of the car, but it's not an efficient transformation, and the engine gets hot, and by that heat is kind of wasted, and basically it's energy that's been extracted from the system. So those are those two ways that you can add or remove energy through, or two examples on when you add energy through heat. Okay. How you add energy through work, it's a little bit weird. Well, it's not weird, but it's not as, we never thought of work in that sense. And in order to understand how we can add work, or how can we add energy through work, we need to explain the kind of energies that we're going to be using. Okay. So far, so good? Is it making sense? Are you still awake? Okay. This is where it went down in the morning. So I'm going to try to do it slowly. So there are different kind of energies that we're going to be working. You are familiar with chemical energy, or the energy that is being stored in chemical reaction or produced by chemical reactions or chemical bonding. So that's one kind of energy. So chemical energy. Okay. There are other kind of energies that are called potential energies. And with potential energy, the ones that we're going to be working are basically three kind of potential energies. One is called gravitational potential energy. Gravitational. The other one is called spring potential energy. And the last one is electric potential energy. All potential energies, we use the letter U to talk about the potential energies. So gravitational will be U sub G, the spring will be U sub S, and electric will be U of E. Okay, we're going to be talking about these two this semester. This one is going to be, for those of you that take 113, we're going to be talking about that one on 113. They're called potential energies for two reasons. One, they're independent of trajectory. Or I guess a path. And they kind of storage. They kind of storage the energy. Okay. The other two energies that we're going to be talking about are kinetic energy. We use the letter capital K. And the last one is thermal energy. And there are different ways that you're going to see it. You're going to see some cases, you're going to see like E sub TH or delta TH. I'm going to try to stay with this one. Okay, so this semester, we're going to be basically talking about gravitational, spring, kinetic, and thermal. Okay. Okay, so I'm going to start trying to describe what is gravitational potential energy. Okay, so imagine that there's a hill and you are at the bottom of the hill and you're trying to roll, you're trying to bring a boulder to the top of the hill. Okay, so you're gonna start pushing this rock and you're gonna start pushing it. You can either carry the ball or you can start pushing it. But eventually what you're gonna do is that you're gonna bring yourself with the Okay, so just by changing the position of the rock, from bringing it from a low level to a high level, you are increasing the energy of the rock. And the energy that you are increasing, or the energy that you are adding, is gravitational potential energy. Is the energy that's been stored in the rock because of the vertical change in position of that rock. Yeah. The way we calculate gravitational potential energy is we use this equation, is the mass of the rock times gravity times the change in height. So if this is my change in height, that's going to be proportional to the amount of energy that I'm adding. The bigger the rock that I'm moving, the more energy I'm also adding. And gravity, obviously, you need to have some gravitational field. We look at the units. So mass is going to be in kilograms. Gravity is meters per second square. And height is going to be also in meters. So kilograms, meters per second square, that's a Newton. And then Newton meter. Okay. If you remember from when we were talking about torque, the units of torque are also Newton meter. It's a little bit confusing, but one of the reasons that we are using energies, or one of the reasons that we work with energies, is because energy is a scalar. So we don't need to work with vectors anymore. So when we are looking at these units, this is the units of a scalar. So we call this a joule. And with a vector and with a torque, torques are vectors, so we keep it Newtons meter, sorry. Okay, so the idea is that when you move this rock up, you were giving this rock from your body, you were giving energy to the rock, and that rock is going to storage that energy as long as it stays in this position. At the moment that this rock, you push it and it starts going downhill, the energy is going to be released. So the lower as it goes downhill, is changing its energy. It's going to be removing its potential energy, and it's going to be transferring to something else. When the rock goes back to the original position, then the change in height is 0 again, and then there's not going to be any gravitational potential energy. Yeah. So the energy that can transfer, that is more obvious to see that transformation, is that as the rock goes down, the velocity is going to start increasing. The rock is going to go faster and faster and faster and faster until it reaches a maximum velocity at the bottom of the hill. So what we have is that we are transferring gravitational potential energy. We are transforming that energy to kinetic energy. Okay, and this is one of the most simple conversions that we can have. You can imagine the opposite. You have a rock, and then you throw it up. So when you throw it up, it's going to have an initial velocity. The rock is going to have a velocity, and as it goes up, the velocity is going to become smaller, 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 smaller. Eventually, it's going to come to a full stop, and then it's going to go down again. So here we go from kinetic energy to gravitational potential energy, and again from gravitational potential energy goes back to kinetic energy. Okay, makes sense? So in order to do these kind of conversions, we need to define what is kinetic energy. Kinetic energy is energy of a body in motion. It doesn't matter the mass of the object. It doesn't matter the speed of the object. Electrons have kinetic energy. Planets have kinetic energies. As long as you're moving, you're going to have kinetic energy. So the way we define kinetic energy is going to be 1/2 of the mass times the square of the velocity. The equation looks completely different from gravitational potential energy. So I'm going to look at the units of kinetic energy. So the 1/2 is just a correction factor that has having dimensions. I have kilograms here, and then the units of velocity is going to be meters per second. But because I have velocity square, I'm going to have meters squared over second square. I can split this and say, well, I'm going to have kilogram meter second square times meter. And this is exactly what we had before. This is going to be again be Newton's meters, which is a joule. Okay, so all energies are going to be measured in joules. Okay, so let's try to do this example. We have a kid is jumping into a pool, and he's jumping from a diving board of 10 meters. So we have the diving board, we have the kid, we have the water, and this is going to be 10 meters. I'm going to need the mass of the kid, and I'm going to say that the mass of the kid, oops, I'm going to say that is 50 kilograms. Okay, so what I want to find out is what is the velocity of the kid when it hits the water. So I want to know what is the velocity when he hits the water. Okay, so the way you solve this kind of problems is, okay, I'm going to transfer, I'm going to be working with two kind of energies. And I'm going to look at the transformation that I'm going to have between these energies. So I'm going to transfer between gravitational potential energy and kinetic energy. Those are the ones that are going to be involved. So the before of this event is the kid standing on the top of the diving board, and the after will be the kid hitting the water. Okay, so the system, I say that is as an isolation, and the way that you can identify that it's in isolation is because there's nothing external to the kid that is adding energy to the system. There's no one pushing down. There's nothing. It doesn't have an engine pulling that goes make it faster. It's everything is already there. It's just the kid standing, and it's just going to be by the effects of gravity that is going to fall. Okay. So in those cases, I know that the initial energy is going to be equal to the final energy. Go. Oh. So the initial energy has to be equal to the final energy. So I'm just going to write down my two energies in terms of initial and final position. So states. So I'm going to have my initial gravitational potential energy. My initial kinetic energy is going to be equal to the final potential energy and the final kinetic energy. Okay, and I'm going to write down here the equations. mg h and kinetic energy is going to be 1/2 mv squared. Yes. Oh, nothing. It's just so you will have initial position or final position depending on where you are. Okay. So when the kid is up here on it's on the diving board, is the kid moving? No. So what is the kinetic energy of the kid? Sylvia? Zero. It doesn't have any kinetic energy. So we can say, okay, the initial kinetic energy is going to be zero. Okay. I'm going to put my frame of reference here at the bottom. Okay. Yeah, so here's my origin. So the initial potential energy is going to be different than zero because with respect to my point of reference, the kid is 10 meters above. So just because of looking at the equation, the kid's going to have a mass, it's going to have, there's gravity, and age is going to be 10 meters. So just because of where the kid is, it's going to have energy. We don't care how the kid got there. We don't care if it was with a helicopter or he climbed a rope or someone picked him up and put it there. We don't care. We only know that because where he is, there's a potential energy on this kid. Now, what will be the height when the kid hits the ground, when the kid hits the water? Zero. So what will be the gravitational potential energy? Zero. So on the right side, this is going to be zero. Okay, so this equation over here basically says all my initial kinetic energy, everything that I had, got transferred into kinetic energy when I hit the ground, when I hit the water. So everything that I have as potential energy transformed into kinetic energy. So from there, I can find out what is the final velocity. And I'm going to do it over here. So the mgh initial equals 1/2 of the mass v final squared. Notice that the masses cancel. So it really doesn't matter what is the mass of the kid. If it's 20 kilograms or it's 100 kilograms, it really doesn't matter. We're going to have GHR equals 1/2 of bf squared. So you can imagine that if you have two objects with different masses, one 10 kilograms and another 100 kilograms, they're going to reach the water at the same time. There's no change in the final velocity just because of the mass. In reality, we don't see that always because there's wind resistance, there's air resistance, and there's drag, and that affects how objects fall. But if you were in vacuum, complete vacuum, and you have a feather and you have a bowling ball, they will both arrive at the same time. And there's a pretty cool video of a guy that is just basically have a huge vacuum chamber, and he does that experiment. And that's actually pretty cool. So from here, I can solve for the final velocity. Now be 2gh initial square root 2 times 9.8 times 10. Sorry. And I get 14 meters per second. Bison, make sense? Sarah, make sense? Any questions? No? In the chat, any questions? Does it make sense so far? Okay, I'm going to assume that was a yes. I don't know if you guys are listening. Wait. Okay. Now you should be able to listen to me a little bit better. Okay. Yeah, makes sense. Now, another thing that is important with gravitational potential energy, because we're ignoring friction right now and we're ignoring drag at this moment, the trajectory, the path that it follows, it doesn't matter. So in this case, I'm assuming that the kid is jumping into a pool, so it's a free fall. But if the kid were going down a slide, as long as this difference is the same, 10 meters, the velocity at the end will be exactly the same. The only thing that I care is the vertical distance, is the change in the vertical distance. I don't care about the changes in the horizontal displacement. So I only care the initial position in the y direction. I only care about the final position in the y direction. So I don't care if the guy is in a roller coaster and he's just doing something kind of weird. If the change in height is 10 meters, it will get to the same velocity. Again, we don't see that in real life because in real life we have friction and that messes up with everything. Okay. Mary, how are you doing?
Great.
Is this exciting?
Pretty good, yeah. I understand it, so it's not confusing.
You see, that's good. At least one person understood so far. In the morning, I'm pretty sure nobody understood anything. Did you understand?
So far.
I said, I just see it. I'm now twice as happy. Okay, so we have seen kinetic energy, we've seen gravitational potential energy. The second one is spring potential energy. So spring potential energy is the energy that is being stored in a spring. So when you compress or stretch a spring, you're gonna have energy storage in that spring. So is the energy when compressing, and I don't know how to spell stretching. We start with an E or it's just S? Stretching?
Yeah.
Okay, thank you. So every time you stretch a spring, every time you compress a spring, the spring is going to be storage energy in there. So imagine that I have a spring, and then you apply a force or something, and the spring is going to compress. Okay, so the amount of compression, delta X, we're going to call it delta X, and the energy inside a spring is going to be 1/2 of K delta X squared. Now, this K is not the same as the one that we were talking about. This is not kinetic energy. This is lowercase k, and this is the spring constant. Okay, be very careful this is one of the most common sources of error. People see the K and they don't make a distinction between kinetic energy and the spring constant, and then everything is a mess. The spring constant is a value that indicates how stiff a spring is going to be. So a slinky has a very low K, and a slinky is very easy to deform. The spring on the suspension of your car is very, very stiff, so the K value is going to be really, really, really high. Okay. K is measured in per meter. Okay. Make sense? So a very common example is, okay, I'm going to have a spring, and on top of the spring, I'm going to put a little marble. And you can imagine that I release the spring, and the marble is just going to be in sheet in the air. It's going to go and reach a maximum height. Okay, and what I want to find out is what is that maximum height. Okay, so I'm gonna add a little bit of information so we can solve this problem. I'm gonna say that the spring constant of the spring, I'm gonna say that this is 100 newtons per meter. I'm gonna say that the marble has a mass of 10 grams. And the compression of the spring, the delta X, I'm going to say that the compression of the spring is 30 centimeters. Okay. Now, a couple of things. The spring constant, this value of K, depends on the geometry of the spring, and it's going to depend also on the materials of the spring. So once the spring is fabricated, it doesn't change. For us, the obvious spring will be our tendons. So the tendons stretch. Some of the muscles also stretch. Well, the muscles also stretch. So they also behave like a spring. So you're also gonna storage energy in the stretching and compression of tendons. Okay, so so if you want to know what is the energy that's being stored in a tendon, it's gonna be exactly the same equation. The K is going to be different because that K is going to be depending on the particular tendon that you have, but it's going to be exactly the same equation. Okay. So in this case, I'm going to be working with two kinds of energy. I'm going to be working with the spring potential energy, and I'm going to be working with gravitational potential energy. Okay, so I'm transforming one into the other. Okay, so I'm going to assume that the energy is conserved. And that will be pretty much always, unless you have some kind of drag or some kind of friction, you can always assume that the energy is going to be conserved. And my initial energy is going to be my initial spring potential energy plus my initial gravitational energy. And the final will be the final spring potential energy and the final gravitational potential energy. Okay. I'm gonna set up a frame of reference just so I can measure the height. And I'm gonna measure the reference right there, where the initial position of the marble. So, okay, yeah, before you fall asleep. So what will be the initial gravitational potential energy?
Is it gonna be the 10 grams?
So the gravitational potential energy, I'm gonna write the equations over here, is the mass times gravity times the height. So what will be the initial gravitational potential energy? So what will be the initial position of the ball? 0. So what will be the initial gravitational potential energy? 0. Yeah? Makes sense? So this is going to be 0. Elizabeth, you're falling asleep. Yeah. Okay, what will be the final potential? What will be the final spring potential energy? There's going to be what? Nope. Sylvia? Why? Yes. It's 0. It's 0. Yes, it's 0. Why? Can someone tell me why, Sarah?
Because it's like not being compressed.
The spring is not compressed anymore. At the moment that the marble is in the air, you can assume that the spring is not compressed anymore. So it lost all the energy that it had storage. So the final spring potential energy is going to be 0. So the equation that simplify that the initial spring energy, everything that was in that spring, now is going to be transformed into gravitational potential energy. Okay, and now I can write the equation. So the initial spring energy is going to be 1/2 of k delta x squared. I forgot the square. And the gravitational potential energy is going to be mgh. And this final height is going to be my maximum height. That's what I want to find out. Okay, so from here I can solve for h max. So I will have k delta x squared over 2 mg. If I didn't, and then from here I can just substitute values. So I'm going to have 100 newtons per meter. Delta x will be 30 centimeters, but you need to work with meters. So here will be 0.3 square. The mass has to be in kilograms, so that will be 0.01 kilograms. And then gravity, 9.8 meters per second square. And I end up with 45.9 meters. Oh, yeah, 45.9. Yeah. Yes.
For your, oh wait, never mind.
Are you sure?
Yeah.
Elizabeth? Makes sense? Yes.
Are we ever gonna have a situation where like one of the terms doesn't cancel out?
Yeah, we'll do an example. Oh, we'll do it now. We'll do it now. Okay, so yes, I mean, do you guys like roller coasters? Yeah. So imagine that you have a roller coaster that's doing something like this. This is supposed to be this, yeah, small loop. There you go. Okay, so we're gonna be here at the top of the roller coaster, and I'm gonna say that this height is gonna be 20 meters. This the diameter of the loop, I'm gonna say that that's 10 meters, and this is gonna be 30 meters. Okay, the mass of the car with the person, I'm gonna say that that's 150 kilograms. And I'm gonna say that actually the car here has some velocity. I'm gonna say, okay, the velocity here is gonna have, I'm gonna say 5 meters per second. So not a lot of velocity, but some velocity. So I'm gonna call this point 1, this is gonna be point 2, this is gonna be point 3. So I want to know what is the velocity at point 2, and I want to know what is the velocity at point 3. Oops. Okay, so I'm gonna do between 1 and 2 first, and then I'm gonna let you guys do between 1 and 3 or between 2 and 3. Okay, so between 1 and 3, again, I'm transforming kinetic and gravitational energy from point 1 to point 2. There's no spring, so there's no spring potential energy, and we haven't talked about friction, so we only have those two. So the energy at 1 has to be equal to the energy at point 2. Okay, now we're gonna have, if we are measuring our height with respect to the ground, so this kid with on the roller coaster at the top is gonna, at point 1, is gonna have some potential energy because the height is gonna be 10, and it has some kinetic energy because it's moving. So none of these are gonna be 0. And point number 2, well, it's gonna be somewhere in this loop. It's gonna be on the top of the loop. So it's gonna have some potential energy, and it's also probably gonna be moving. So again, we're not gonna have 0 in any of those cases, okay? So let's just calculate what would be the velocity here at the top of that loop, okay? So I'm gonna have the mass is gonna be 150 kilograms times 9.8 times 20. And then the kinetic energy is gonna be 1/2 of the mass, 150, times the velocity square, which is 5 meters per second square. And then this is gonna be, at point number 2, we're gonna have 150 kilograms, 1.8 times 10, And then the kinetic energy is just going to be something like that. So we don't know what is V2. We can cancel the masses in all of these. Notice that every single term is multiplied by 150. So it's multiplied by the mass. So we can cancel that. So this, and this. Just be careful. Sometimes, especially if you're working with springs, you cannot cancel the masses. But if you are working with kinetic energies and gravitational potential energies, usually you can cancel the masses. So you're going to have 9.8 plus 20, 1/2 of 5 squared, 9.8, 10, and 1/2 v squared. Oops, this is plus. Okay, so here I'm just going to do a little bit of algebra. Okay, and with 42.3 equals 9.8 10. Oh. No, I did something wrong. $208.5. Yeah. Say that again. So, 98. I just already multiplied the 9.8 instead. Yeah. Makes sense. Okay. So we're going to stop here, and then tomorrow we'll do the last part from 1 to 3. Okay. Any questions so far? No. Okay. Well, that's it. Thank you so much. See you guys on Wednesday.